Hello class, and thank you for watching. In topic 1.10, rational functions and wholes, you're going to determine the location of a whole on the graph of a rational function and distinguish it from vertical isotopes. Now in the previous lesson, we talked about vertical isotopes and how that correlates again to the domain. All the values of x are excluded again from the function because it makes the denominator equal to 0. Well, we're going to look at the exact same situation, but this time we're going to look at the situation where the the domain value matches again with the factor of the numerator. So a whole and rational function exists when factors in the numerator cancels out with the factors in the denominator. So for example, let's look at this example that we have right here, okay? First of all, if you look on the top, notice that we cross the x-axis. According to this, we should have zeros when the numerator is equal to 0, okay? So when x minus 1 is equal to 0, that would be at x equals to positive 1. Let me erase this and let me get a thicker pen here. So when x, that's a little bit too thick. What's this? 2, let's do 3, okay. So let's look at this, okay? So again, we know that when our numerator is equal to 0, when this right here is equal to 0, when x minus 1 is equal to 0, and when x minus 3 is equal to 0, which is x equals to positive 1 and x equals to positive 3, those are going to be our x-intercepts. Those are going to be our zeros. This is where we're crossing the x-axis. Well, I can clearly see that I'm crossing the x-axis at positive 3. This one right here is that point right there in blue. However, x equals to 1 is not an x-intercept. I do not cross the x-axis at 1. Let's see what the reason is. Well, if you look at the denominator, here our denominator, if you look at our denominator here, we see that when our denominator is equal to 0, so when x is equal to 0 and when x minus 1 is equal to 0, we get 0 and positive 1. These numbers again are the numbers that get excluded from the domain, so x cannot equal to those values. And you'll notice that 1 is included in that situation. 1 and 1 right there. So when that occurs, this is what's happening again in today's lesson. We're looking again at this 0. Anytime we have a factor that is common with the numerator, like this one right here, x minus 1 and x minus 1, at those locations, we don't have neither a vertical isotope, nor do we have an x-intercept. Okay, we have neither of those two things. So in this situation, the result is as we end up with a hole in that location, as you see right here, at x equals to positive 1. Okay, as x equals to positive 1, we have a hole in the graph of this function right there. So the hole is the result of having a common factor in the numerator and the denominator every single time. And we're not going to have a 0 on the top, and we're not going to have a vertical isotope as a result in the bottom here. So in this situation here, with the only 0 that we have occurs where x equals positive 3, and let me do this in this color, x equals to positive 3, which is here. And for this one right here, we do not have a vertical isotope at 1. The only vertical isotope that we have is at x equals 0, which is this purple line right there. And since this is a common factor on the numerator and the denominator, I'm going to now do it in blue. At x minus 1 equals to 0, which is the solution of x equals to positive 1, this is the location of a hole. So the only way we can have a 0 is if there is no common factor with the denominator, and the only way we can have a vertical isotope is if there is no common factor with the numerator. But if there is a common factor in the top and on the bottom, that factor set equal to 0 and the solution to that factor is equal to 0 is going to be the location of our hole. Now, these two, this hole and this vertical isotope, are referred to as discontinuities, meaning that the function is not continuous. Function, just like anything else in nature, wants to be connected with something else. So these graphs, again, these rational functions want to be connected through these lines, but because we cannot divide by 0, it naturally breaks apart. And then there's these boundary lines, like this purple one I have right here, or these holes like I see right here, that disconnect the graph at those locations. They prevent it from being continuous and be connected from negative to positive infinity. But again, they try very badly again to be connected. But because we're dividing with 0 when we have x equal to, in this situation, with 1 and 0, then it breaks the graph apart, and it will stop being connected. Hence the term discontinuity. Now, these two type of discontinuities have different names. The vertical isotope is referred to as an infinite discontinuity because the ends are going towards an infinity, either positive or negative infinity. And the holes are referred to as removable discontinuities because all I have to do to remove the discontinuity, remove the hole, is just simply fill it in. If I fill it in, I can see that this thing will have a y value in this situation of -2. So let's first study again the behavior around today's discontinuity, which is a hole. So let's write a limit statement. Here we have another graph for example number 1. We're going to write a left and right limit statement as x approaches the hole, which is located right here. So as x approaches -1. So this again is a hole, aka a removable discontinuity. So our limit, let me get a smaller one here. Let me get a thinner pen. So our limit as x approaches -1, and we'll call this function f of x from the left side, and we want to get the limit as x approaches -1 from the right side. Of f of x. So let's see what these graphs are going to look like. So let's see. So we're going to approach again. This is where 1 is, and we're going to approach the graph from the left side and from the right side along this portion right there, okay? Now, when we approach a hole, the limit value as we approach a hole from the left and the right is always going to match up because this hole is removable, and all I have to do to remove this hole is to fill that hole in. And as a result, that's going to be a y value that would be again the coordinate for that hole right there. So the hole has a coordinate of -1 and 2. So if I approach this hole from both the left and right value, they're going to give me the same answer. From the left, it's going to get to the y value of 2, and from the right, it's going to also equal to that y value of 2. So very similar to the horizontal isotope, where the ends again approach this horizontal line. When we approach a hole, a removable discontinuity, the answer is going to be the same from both the left and the right end of that discontinuity of that hole. So right here, this is what the left hand behavior and the right hand behavior as x approaches -1 is. Let's see, let's move on to another example, and let's look at distinguishing the difference between a hole and a vertical isotope. So for numbers, for example 2, for each function below, we're going to determine the x values for any holes or vertical isotopes. And we're also going to look at how we're going to write a limit statement describing the behavior as x approaches the holes on this function. So to find the vertical isotope, that's going to be the result again that is where our numerator and denominator does not have a common factor. So I'm going to look at the bottom, okay, these two things right here, and I'm just going to simply focus on the one that doesn't match with the top. So from the bottom one, we have x minus 5 and x plus 3. But since there's an x plus 3 on the top, the x plus 3 set equal to 0 is going to be the location for our hole. So solving this equation by moving the 3 to the other side tells me that x is equal to 3. So this is where the hole is going to be located at when x equals 3. To figure out the vertical isotope, I simply now look at the one that doesn't match up with the top, that doesn't have a common factor. X minus 5 doesn't match up with anything up there. So this is going to be our vertical isotope. So solving the equation, and I'm going to do it in blue instead of red, x plus 5 equal to 0. Solving this equation is going to tell me the location of the vertical isotope. So x equals to negative 5 is our vertical isotope. Now let's look at the behavior. Since we practiced this one the other lesson, let's now practice this. What's going to happen as x approaches 3? Because it's a hole, all I have to do in order to fill a hole is to factor out the common factor. So instead of having f of x equal to x minus 2 and x plus 3, I'm going to now have f of x equal only to x minus 2 and x minus 5. By reducing out this common factor, I have filled in the hole in the graph that's occurring at x equals to 3. Okay, I'm just going to fill in that hole at x equals to 3, wherever that value is. So to find the limit as x approaches 3 from the left side of f of x, and to find the limit as x approaches 3 from the right side of f of x, all I need to do is simply test what happens now when I plug in the 3. Since I filled in the hole and there is no more plus 3, I'm sorry, this should be minus 3. I just saw it right now. And x plus 3, the solution would be x equals negative 3. So that's the location of the hole. So let's fix this. And let's find the limit behavior as x approaches negative 3 from the left side. And let's find the limit as x approaches negative 3 from the right side. So by factoring out or reducing the common factor of x plus 3 from the numerator and denominator, we have filled in the hole. And now we can focus on this right here. And instead of testing numbers to the left of negative 3 and testing numbers to the right of negative 3, since there is no more x plus 3, I'm not going to get 0 by using negative 3. I'm going to simply plug that into the x on the top and on the bottom. So I'm going to plug in negative 3 here and there. So I'm going to evaluate f when x is equal to negative 3. So if I do negative 3 minus 2 and negative 3 minus 5, this is going to be negative 5 over a negative 8. And that's going to reduce to 5 over 8. So if I fill in the hole at x equals to negative 3, the y value is now going to be 5 over 3. If I don't fill in that hole and I keep f of x as x minus 2 times x plus 3 over x minus 5 and x plus 3, when I evaluate this at negative 3, negative 3 minus 2, negative 3 plus 3, and negative 3 minus 5, and negative 3 plus 3, these two values I'm going to highlight right here in yellow are going to equal to 0. So this 0 times whatever this is going to be 0, and the same thing on the bottom. This 0 right here in the bottom, I'm going to highlight now in gray, times this 0 right here in red, that's going to equal to 0. So I'm going to end up with 0 over 0, which cannot be defined. But if I factor it out, I have filled in the hole, and when I now plug in negative 3, I get that the y value is going to be 5 over 3. So the limit behavior as x approaches this hole is going to equal to the value of 5 over 8. Not over 3, I misspoke, I meant 5 over 8. So that's going to be your answer. So the behavior as x approaches a hole on a rational function is going to equal to a numerical value instead of positive or negative infinity. So let's look at another example. Let me erase this and let's look at another example, okay? So first let's distinguish on example B where the vertical isotope is and where the hole is. Now notice we have factors here, okay? So let's see what we have here. We have an x plus 1. We have two x minus 2's. We have an x minus 2 and two x plus 1's. Okay. The first thing I'm going to look at is see how many factors we have of each, if there's anything on top that matches with the bottom. Again, to find the vertical isotope in the holes, I focus on the bottom. As long as it doesn't match up with the top, it's going to be a vertical isotope, but if it matches with the top, it's going to be a hole. So right here, notice again, this x minus 2 matches with the one on top. So this is going to be a hole. So x minus 2 is equal to 0 is going to be the location of the hole. So solving this equation by moving the 2 to the other side means that x equals to positive 2. So that's going to be the location of the hole. Now if I factor that hole out, if I fill in that hole by factoring this out and dividing these out, that's going to give me again 1. So this reduces out. And h of x will now be x plus 1 times x minus 2 over x plus 1 times x plus 1. So let's look at the limit as x approaches 2 from the left and as x approaches 2 from the right. So now that I filled in that hole, the limit as we approach this hole is going to end up equaling to a y value, and to find that y value, we're now simply going to plug in this 2 into my function, having taken out and filled in that hole. So we're going to figure out what h of 2 equals. So this would be 2 plus 1, 2 minus 2 over 2 plus 1 times 2 plus 1. 2 plus 1 is 3, 2 minus 2 is 0, 2 plus 1 is 3, and 2 plus 1 again is 3. On the top we end up with 0, on the bottom we end up with 9, and 0 divided by 9 is equal to 0. So the limit behavior as we approach this hole means that the y value is going to get close to 0 when we fill it in, and we factor out the common factor when we fill in the hole. And that's going to be true again from both sides. So this is the behavior as we approach that value. Now, let's talk about the other one, okay? Now, x plus 1, we have two of those. Those would be the location of vertical isotopes as long as they don't match up with the top. And well, one of them does, okay? One of them does match up with the top. But if I factor out that value and I factor out this x plus 1 with only one of them, so this one, let's say this one with this one, we still have an x minus 1 on the bottom. So since this one doesn't match up with anything else, there's no hole to fill in with this one. So we're going to end up with a vertical isotope at x plus 1. So if I get x plus 1 and set it equal to 0, we have a vertical isotope at that location. All of these values are considered again discontinuities, but a hole occurs when it matches up with one of them on the top, and a vertical isotope is when it doesn't match up. So even though this x plus 1 matches up with the one x plus 1 on top there, there's still going to be one left over, and because that one doesn't match up, that means we're going to end up with a vertical isotope at that location. So if I get x plus 1 and equal it to 0, solving this equation, x equals to negative 1, this is going to be the location of the vertical isotope. And we're not going to look at how this graph behaves because that was the objective of the previous lesson, okay? So we won't practice that one right here. We're going to only focus on writing the limit notation as x approaches, again, a hole, not a vertical isotope. Let's see. Let's now look at example 3. Let's write a left-hand and right-hand limit statement as x approaches 2 for each of the following functions, okay? So let's first look at what's happening again at 2. Well, the only thing that we care about at 2, if it's going to be a vertical isotope or a hole. So let's look at the bottom. We look at the bottom here. We see that x minus 2 does not match up with anything on top. Because of that, this discontinuity at x minus 2 is equal to 0 means that we're going to have a vertical isotope at that location. So solving the equation for x by adding 2 to both sides tells us that x is going to equal to positive 2. So this is where our vertical isotope is going to be at. So let's see what happens as x approaches the vertical isotope of 2 from negative from the left side, and as x approaches positive 2 from the right side. Now recall, I'm going to draw myself an x and y axis, and we have a vertical isotope at 2. So there's this imaginary vertical line at x equals 2. So it's a boundary line that's going to disconnect the graph, and one of two things can happen. From the left end, the graph can try to move up, trying to connect to the right end, but because of the boundary line, it's going to simply move up. Or it could go this way towards the red boundary line, and because again of the boundary line, it can move down. And then the same thing from the other side. From the right side of this boundary line, we can go towards it and move up towards positive infinity, or we can move towards it and move downwards towards negative infinity. So one of the two things is going to happen on the top, on the left side, either pointing up or pointing down, and the same thing on the right side, pointing up or pointing down. Well, to figure out what is happening there, what we're going to do is that we're going to test a point that's going to be extremely close to the number 2. So on the left side, I'm going to use the number 1.9. That's really close to the number 2. And on the right side, I'm going to use the number 2.1. That's really close to the number 2. And we're going to plug those numbers in to our function right there. So if I plug in 1.9 into the first parentheses, 1.9 minus 1, that's going to be a positive value. 1.9 plus 3, that's going to be a positive value. And 1.9 minus 2, that's going to be a negative value. So this negative value doesn't match up with anything, so the entire thing is going to be negative on the left end. So because it's negative, that means that the left end is pointing downwards. So the left end is going to go towards negative infinity. So the left limit statement of the function as x approaches the vertical isotope of 2 from the left, I know I said that twice, that's going to be negative infinity. Now let's see what happens as x approaches the vertical isotope of 2 from the right side. So from the right, we're going to pick a number very close to 2, so we're going to pick 2.1. And if I do 2.1 minus 1, that's going to be a positive number in the first parentheses up here. If I do 2.1 plus 3, that's a positive value as well. And in the denominator, if I do 2.1 minus 2, that's going to be a positive value. So this equals to positive. So the right end is pointing upwards towards positive infinity. So there's your answer. So now let's look at the next one. For this one right here. Again, we want to write a limit statement as x approaches 2 from the left, and we want to see what happens as x approaches 2 from the right to this function. Well, remember, two things can happen. If it's approaching a vertical isotope, if x equals 2 is a vertical isotope, then it's going to go towards the infinities, positive or negative. But if we're approaching a whole, then it's going to approach a y value, which can be found by filling in the hole and plugging in again the value of x, which in this case would be x equals to 2. So the first thing we need to do is figure out what's happening at that location. So let's factor out and let's see what we have. So we have an x minus 2, and there's two of them. So x minus 2 and x minus 2. We have an x plus 4, and we have an x minus 2 with an x minus 3. Remember, a whole happens when the factor in the numerator cancels out a factor in the denominator. So that's exactly what's happening here. At x minus 2, all right, this factors out with that value right there. So because this x minus 2 reduces with this one right there, that means that x minus 2 equals to 0. That's going to be a coordinate of the whole. And when I add 2 to both sides to solve this equation for x, I see that x equals 2 is the location of the whole. Now I know there's another x minus 2 on the top, but this one, it needs to only reduce with one of them on top. So as long as this reduces with one of them on top, then we're going to end up a whole. Notice that x minus 3 doesn't match up with anything there. So at x minus 3 equals to 0, that's going to be a vertical isotope. So since we have that, we have a whole at x equals to 2, we're going to fill in the hole by reducing this out and having f of x equal to x minus 2, x plus 4, and x minus 3 in the bottom. And to figure out the limit statement as we approach 2 from the left and from the right, we're simply now going to plug in the number 2 here for the values of x and figure out what the y value would be when x is equal to 2. So I do 2 minus 2 times 2 plus 4 over 2 minus 3. I'm going to get 0 on the top, 6 on the top, and negative 1 on the bottom. And 0 divided by negative 1 equals 0. So the left end and the right end are approaching 0. Okay. Let's now work backwards, and let's come up with a function given the equation when we have zeros, wholes, and vertical isotopes. Let's first talk about the zeros and recall 0. A 0 is when we cross the x-axis, and that occurs when our numerator function is equal to 0. So here we see that our numerator function equals to 0 when the value of x equals to positive 2. So if x is equal to positive 2, that means that the numerator, we have to have something that will give us 2. Well, to give us a positive 2, that means that x minus 2 would have to equal to 0. So our factor would be x minus 2. So our function, I'll call it r of x, has to have a numerator of x minus 2 in order to cross the x-axis at this location there. Now, in order to have a vertical isotope, like we see right here, at negative 3, at x equals negative 3, our denominator, d of x, that has to equal to 0. Well, in order for d of x to equal to 0, as you see right here, x has to equal to negative 3. Well, how can we get an expression to give us an answer of negative 3? Well, we would have to get x, add 3 to it, and have that equal to 0, which means that our factor would be x plus 3. So we would have to have an x plus 3 in the denominator. Now, in order to have a whole in our function, we need to have a common factor in the numerator and in the denominator. We need to have the same factor on the top and on the bottom. Well, we see that the x value of our whole is x equals negative 4. Well, the only way to get x equal negative 4 in the numerator and in the denominator is if x plus 4 was equal to 0. So that means that our factor would have to be x plus 4. And since it's a whole, that's going to be a common factor in the numerator and in the denominator. So simply reverse engineering this and understanding that we have wholes when our numerator and our denominator matches. We have a vertical isotope when our denominator doesn't match up with the numerator, and we have a 0 when our numerator doesn't match up with our denominator. So this would be the equation to represent this concept right here, where we have a 0 at 2, a vertical isotope at negative 3, and a whole at x equals negative 4. So let's look at another example. So for this example, same situation. We'll start by first identifying our 0. Well, we cross the x-axis at negative 2. And since x equals negative 2, that means that x plus 2 would be the equation that gives us, again, that answer. Again, we're just simply re-engineering this, reverse engineering this. So x plus 2 would have to equal to 0, which means that x plus 2 would be the factor that we would find in the numerator. So we would have an x plus 2 in the numerator to have an x-axis or an x-intercept at negative 2. Now our vertical isotope occurs again when the denominator is equal to 0. So here's the vertical isotope, which is at x equals positive 1. In order for x to equal to 1, that means that x would have to be subtracted by 1 and set equal to 0. Which means that x minus 1 would be the factor that we would have in our denominator. And to find the whole, well, our whole is the result of having a common factor in the numerator and the denominator. And we see that this whole is located at x is equal to 0. That's the x coordinate to this whole. So x equal to 0 means that x minus 0 would have to be set at equal to 0, and our factor would be x minus 0. Which is just x. X minus 0 is just a term of x. And we would have to have it in the numerator and the denominator in order to have a whole at that location. So this would be the equation that represents the graph that has a whole at 0, a x-intercept at negative 2, and a vertical isotope at x equals positive 1. Now let's do the same thing, but using limit notations. So using limit notation, this is going to be really important to distinguish the difference when we have a whole and when we have a vertical isotope. With limit notations, if we are approaching a whole number like 3 or any number like we have right here, and the answer is another whole number, this is just basically telling us what the x and y values are. So right here, as x approaches 3 from the left side and x approaches 3 from the right side, okay, my answer is 5. So that means that we have the point 3, 5. So this is a whole. This is just simply telling me the coordinate of a whole. And to have a whole, well, I need x to equal to 3 because that's where we're approaching, which means that x minus 3 would have to be set equal to 0, which our factor would be x minus 3. So we have to have an x minus 3 in the numerator and an x minus 3 in the denominator in order to have a whole. Now, in order to have a vertical isotope, our limit as it approaches an integer from the left and from the right, fix this. This is an error. There should be a plus sign right here. Okay. And they go to infinity. That means that we have a vertical isotope whenever we approach a number and we're going to the infinities, whether it's both negative, both positive, or one's negative, one's positive. That means we have a vertical isotope. And since we're approaching x equals to 1, that means that the vertical isotope is at x equals 1, which means that the factor would have to be x minus 1. And because it's a vertical isotope, that's only going to be found in the bottom. So the equation where the limit as x approaches 3 is the whole number 5 would be a whole. So we would have to need that on both locations. And the limit as x approaches 1 goes to the infinities, and infinite discontinuity That would be a vertical isotope, which that factor is only found in the bottom. So let's try one more, okay? So again, the same idea. Remember, a whole is the result that there's a common factor in the numerator and denominator of our rational function. And the limit notation for that is represented and identified when we approach a number like -2 from the left and from the right, and the limit of that equals to a whole number. So since the limit of f of x equals to 4 when we approach -2 from the right and from the end, that means that we have a whole at x equals -2. And if that's the location of the whole, that means the only way to get x equal to -2 is if x was being added with 2 to get 0, and that's going to be our factor, x plus 2. To have a vertical isotope, the limit as we approach a number, which in this case is -1, has to go to the infinities. And this again should be a plus, not a minus. That's a typo on my end. And it doesn't matter that they're going to different infinities, like this one's going to positive and this one's going to positive. But because they go to the infinities, that means that at x equals 1, there is a vertical isotope there. And if x is going to equal to 1, that means that x had to be subtracted from 1 when set to 0. So that means that x minus 1 would have to be the factor. So all we're doing again is using the information and just reverse engineering as working backwards from this to see what the function will look like. Of course, there could be more functions. We could have intercepts, but we don't know again what the intercepts are. So to writing an equation just to fit in again, writing any equation of a rational function just to fit this again limit properties would just be those quantities there. Okay. Oh, hold on, I messed up, because if I only have x plus 2, I almost messed up on this one. If I only have an x plus 2 right there, this would be a 0 and not a whole. In order to have a whole at x equals -2, I need to have an x plus 2 on the top and an x plus 2 on the bottom. There needs to be that common factor there. Because if I only have the x plus 2 on the top, then that's going to be an x-intercept, a 0, a place where we cross the x-axis. So I need to have it both on top and on the bottom. Okay, there I fixed it. All right, and that concludes our notes on wholes on a rational function. If you have any questions, please make sure to write them down and prepare to discuss them again tomorrow. Like always, I appreciate you watching, and I hope you have a great day. Goodbye.